Okay, so today we are going to see the practice Python example for linear regression with one variable. So we will
Hmm.
start with the data set. Uh, I will show you what is the data set on which we are going to work. Okay, so
Okay.
this is
Okay.
this is our data set. If you see this data set, it
Yeah,
has
you mailed me. Yeah.
yeah I have made you. It has basically 96 rows where
Okay.
where each row have two columns. So if I actually tell, it is basically a matrix of 96 into 2. Great. So this is our data set on which we will be seeing how the linear regression works. Okay. Now
Yeah.
in this particular data set, the first column is basically the population of the city. Population of the
Hmm. Yes.
city. And the second column is basically the profit of the outlet. Profit of
Okay.
outlet, and this particular data, 96 data point, I have with me. I mean, it's a historical data. It's a historical
Okay.
data. I mean, previously known data. This will be our training data, on which we will be trying to, uh, on which we will try to uh, do linear regression and fit a line to get the trend basically. Okay, so as
Okay.
I yeah so as I told you, this uh, this is basically Python console, right? Here this is
Hmm.
Python editor, and here you have this IPython console where you can run program, or you can, if any output will come, it will come here only. So I
Yes.
will show you how the program looks like. Yeah. So linear regression, one variable. Yes. Okay. Good enough. So this is basically a Python example to build the linear regression. So what I will do, just for practice, or you can say just for, I will make a test file kind of thing. Okay. So what I
Hmm.
will
Okay.
do, yeah, I will make a test.py maybe,
Okay.
and I will try. What we will do, we will make a test file and we will try to build this file from scratch. I mean, I already have this build file, but rather than going through a step by step, maybe once you are acquainted with Python programming, then it will be better.
Hmm.
Then I can maybe show you just the code. But as of now, yet I think maybe for the first practice example, I will show you how to code, and then you can maybe do it on your own. And once you are acquainted, then maybe yeah, we can see the codes directly. So the first thing is,
Okay.
yeah. So the first thing is, how can we read this file? This particular file we have to read. So I will take a file pointer fp. This is very similar to what we used to do in Java or Python, or you might be doing in your Objective C++ or something, right? So
Hmm.
this is the file name ex1 data1. If you see this file name ex1 data1, this is in the current
Okay.
directory, and this test.py which I am making is also in the same directory. So I can just
Okay.
write ex1 data1, and in read mode I have to read this file. Once I read this file, what I need to do is I want to check that I want to read this into some variable, and I want to check whether it is coming or not, right? So with this, I mean, in
Hmm.
Python, how do you do that? You have to just make a for loop. Say for line in fp. fp is my file pointer. So you can just try printing this line. It will read line by line. I mean, it should read.
Okay.
You see, in the output console, you can see it has read the
Mm.
I will open a new dedicated Python console for this program test.py. Now you can see all the data points, all the 96 data point has come onto the come on, I mean in this file it is coming, right? That's why it in loop it is printing all these 96 here, right? But right now
Okay.
it is in a string format. As whatever you write in a file, even if you write integer, it will be stored as a string, right? So it is printing right now as a line with this comma and all, right? And also you see,
Mm.
because every file, at the end there is a slash n character, new line character. When you,
Yes.
yeah, when you do an enter, basically what happens, a new line character is getting printed. That is why you see
Okay.
in here in a spider, you see in between uh, every two line there is a slash n also. I mean there is a, in between there is a line also. Okay, so if you want to
Mm.
remove this slash n, and so that this extra line will go off, just I am doing just like that. I mean, even if you don't know, do it, it will work, but I am just doing like that. So there is this strip function. Strip function will do what? It will, the same line I am going to strip, so it will remove the slash n, the new line character from there. Okay, so now if I run it, you see the in between lines and has gone, right? It's a continuous line, right? Now,
Okay.
the second thing, now the question here is that this is a line with two float values, separated by a comma. I want to read them
Mm.
in variable, right? As I told you,
Mm.
this is by basically my x, the population, and this is my basically y, the amount of profit I am going to have, right? You can say that of course the
Okay.
profit of outlet will depend upon various variables, various features, not only the population of the city, but how the crowd is, what is the maybe average income of the people residing over the city, I mean in that city. So those things will also affect. But yeah, this is linear regression with single variable. So we are going to capture the linear relationship between one variable x and the outcome y. So
Okay.
now we are going to do what line. Say maybe I will take a row variable. Just each row, for each row I am taking another variable row, and I am doing line dot split. Why I am doing this split? So that I can, in the split you have to give the character from where you want to split it. So I am basically taking this comma. So through comma you have to split it. That's the funda. So whatever, like
Yes.
whatever, however, how many times there will be comma, it will split from there. So if it will split here each line, after splitting there will be two values. One will be this and another will be
Mm.
this. Okay. Yeah.
Yes.
So now this, if you see this row, if I will print this row now, this row becomes a list now. So in the earlier
Mm.
session we have seen how the list looks like. It will be simply two values. So if you see now, you see these values have become a list. So basically this is the row 0 and this is row 1. Then this is row 0, then this is row 1. You do nothing. Suppose I do break
Okay.
here. Suppose I put a break here, it will just print the first value. See?
Okay.
If I print is row 0, comma, row 1, see it will print the values, just the values. So you can get each value you can get separately now. If I
Okay.
remove the break and run it again, you will get your whole data. You see?
Mm. Mm.
Okay. And if you will directly print row, just row, if you will print, it will print
List
as a
values.
list here. So anyway, so the main purpose here is I have to separate out the x and y, because x is my feature and y is the
Mm.
result outcome. So first I have to somehow take the arrays there, right? We have to separate out the arrays. So what I will do, I will take a X array and I will take a Y array. Two arrays I will take. Now, how do I take array in Python? We have seen this some day, some
Zeros.
in previous day, that np.zeros
Yeah.
and you give the dimension. So as I have 96 data point, I will give the dimension like this
Okay.
for X and similarly for Y. Okay. So these are the two
Okay.
variables which I have made. Now basically x of I, at x of I have to put row 0. So while
Mm-hmm.
iterating through this loop, if you see, while iterating through this loop, each row 0 will be this and row 1 will be this. Right? Right now we saw,
Yes.
right? When you this acts as a list, right? So when you take row
Mm-hmm.
0, this row 0 will go in xi, in the first position of
Mm-hmm.
x. Okay. And
Okay.
and, and row 1 should go in y basically. It should go in y array, isn't it? It should go in y
Mm.
array. Row 1. It should go in y array. Now the question here is that what is my I here? I should be some iterator, isn't it? I
Mm.
should be some iterator
Yes.
which will be 1, 2, 3, 4, 5 till 96 it will be capturing. So how do you put
Yes.
an iterator in the Python? Because here the
Mm.
line is basically you know taking the elements from FP. I mean line by line it is read in the from the FP file pointer. So what we have seen in
Yes.
initially, that if you want to get a iterator in Python, just in the for loop, just enumerate it. So when you enumerate it,
Enumerate.
you can take this particular I here, which will be 0, 1, 2, 3, like that it will go. Now this I
Okay.
seems logically fine, right? So this way you can
Yes.
basically easily build your X and you have made your Y. So this things have built. Now this error will come here. Okay. Now what is the error saying?
NumPy.
It is saying that you don't have
And
imported NumPy. So what you have to do? You have to import NumPy as NP, right?
and
So,
okay.
so now if you see this Y and X has been printed, of course they have been printed sequentially. So this is maybe your till here, till here is your X, and from here it is your
Okay.
Y. Okay. Anyway,
Okay.
so right now basically we saw that okay we have got our X and Y. So if you remember the theories,
Yes.
whatever theories we have done in the last session, we have seen lot of theories. So how do we say our hypothesis? How do we represent our hypothesis? We represent like this, right? Which is basically theta naught plus theta 1 x. And
Mm.
this hypothesis is basically I also represent it by sometime y hat, y predicted value. Right now,
Yeah.
what are the things we have? That from the historical data I have y. This is the predicted. This is the predicted thing, right? This
Yes.
is actual.
Actual.
So
Actual.
right now I have actual y and I have actual x also, right? These two
Yes.
things we have. Now we can perform linear regression in here, okay? With these two
Mm.
things, maybe, right?
Okay.
Yeah. So basically, what I'm going to do, I'm going to uh, the sklearn website, the sklearn library we have seen. From there, I will be importing this linear regression function, linear regression model. Okay. So what I will do,
Okay.
I will do say from sklearn. Okay. So from sklearn, import. I suppose here sklearn and then again there is a package linear model. Import linear regression. Good enough? I see
Yes.
this from this package import this function, this class, sorry. So this class linear regression which already have been implemented there for you, this particular linear regression model we have imported. Now we don't have to do anything. Just initialize this class. You remember initialization? I mean, in OOPS we what do we call it? We will make an object of the class. Uh,
Hmm. Yes,
that's
yes,
what do we call it? Like constructor calling, right? We will initialize the
yes.
constructor. So it is similar
Yes.
concept here that linear regression is a
Hmm.
class. So basically, right now we are initializing our class. We are calling the constructor here. So that
Okay.
is fine. I mean, right now we don't have to worry about any of the parameters in linear regression. We will just call the default constructor whatever it is there, right? And then
Okay.
you have to train the model. So in general, what this sklearn people have done, this scikit-learn people uses this fit function. Fit function means training. For all the model, they have, they have carried the same nomenclature. They have kept the same nomenclature. So most of the time, you will find this fit. Not all the time, yeah, but most of the time, you will find this fit function, which does the training thing. Okay, so this particular function will be performing the gradient descent part and all those things for you, right? So here,
Okay.
but here, what do we have to pass? We have to pass our x and we have to pass our y, because these two
Okay.
parameters will be, see, in the gradient descent, if you remember, we have seen that you start from any random position theta naught and theta 1. So when I am saying you start from any random position theta naught and theta 1, you theta naught and theta 1 you do not need to give it to the function, or this fit function, because theta naught and theta 1 it will randomly start from somewhere. What do you need to give? And once the theta naught and theta 1 are chosen randomly, you can calculate the y predict also by theta naught plus theta 1 x formula. You can calculate the y predict. What needs to be given is, for calculating the cost function, you should know y actual. What was my y actual? Then only you will be able to calculate the cost function. If you remember the cost function that was represented by j theta naught j theta 1, this was something like this, right?
Summation of 1 to n,
Yeah,
1 by 2n,
yeah, 1 by 2n of
and
course, but usually,
2n.
yeah. So 1 by 2n, and then what? Y actual
Uh,
minus
then
y
y actual
predicted
and y predicted
square, right?
square root square.
So
Yes.
this was the cost function. So here the actual y will be required. So that's why we need to
Hmm.
pass actual y, and of course x also will
Hmm.
we need to pass, so that we can calculate the y predict.
Hmm.
For calculating y predict, we need to pass the x. So these two parameters we will be
Okay.
passing in the fit function, and
Okay.
this two line will do the all the theories which we have studied yesterday. These two line will be able to do. Good enough. Now,
Okay.
now, once this is done, you would like to see what is the equation of line it has finally come up with, isn't it? So I will just
Yes.
print equation of line. This is just for printing, and then there is something. This model, the same model which I have trained. This has something called
Hmm.
as intercept. Intercept
Okay.
is what?
Yes.
Intercept is basically the theta naught, and
Theta not x y
the same function will have something called
slope.
as, yeah. So I did plus theta naught plus then model
Plus
dot,
slope.
and then it has something called as coef, right? This is basically the
Okay.
coefficient 0.
Coefficient.
So this is my theta 1. Okay, so theta naught plus theta
Hmm.
1, and yeah, and of course the
X
x.
x.
So this is going to be your line. If I run this program,
Hmm.
you will find that after model fitting, it is now, right now it is doing model fitting. It will come up with the equation model intercept and
It
coef.
is
Yeah,
processing.
yeah.
Okay.
So now the processing has been complete. You can see your equation of line. Okay.
Okay.
Yeah.
Okay.
So yeah, you can see the equation of line. I can maybe put a star over here so that it will be, yeah. So this is the basically the equation of the line which it has learned. This is the theta naught and this is the theta one. Right?
Okay.
Now,
Okay.
yeah. So now if you got the equation of the line, you can see now you will say that how is this intercept and what is this coefficient? How is this coming? So you will you will say that okay, how do I know how what are the parameters and all? Because you are telling me that's fine, but how should I know if I want to see? So that's what I told you. It's very easy. Just type Scalar and the model name. You the first link which where you go is basically telling you the implementation of this, right? So linear regression and this all things are there. Now you see the attributes. Always see the
Hmm.
attributes. What are the attributes which you can display, which you can print, which this object carries. So if you remember the simple OOPS program, object oriented programming language, if you see, we
Yes.
usually we used to have what we study in college. We have class student,
Hmm.
and then we have something say int id, huh?
Yes.
Then something we have say string name,
Name.
right? And then we have say uh, some some constructor will be there for this student, right?
Hmm.
And then
Yes.
some void get roll number
Function.
or something get roll number or something will be there, right? So basically these id and string are called attributes, right?
Attribute.
These things you can access. If these are public, you can access this. So in Python, these are called attributes, which are you can see for any of the model, any of the machine learning model. You can search through scalar. You can go through these attributes. Here you will find see the independent term in the linear model. That's your theta naught. Coefficients.
Hmm.
Coefficient is basically estimated coefficient for linear regression problem. Now this coefficient is basically an array of shape features. So how many features we have?
96.
No, no, no. 96 is the number of data points. How many features we have
Okay.
in this data set?
Two.
It features is basically your independent variable. So feature is only one. That's
One.
x.
Okay.
X. So
Okay. Okay.
basically,
X.
initially also we discussed that currently we are only learning linear regression with single variable. So single variable means only one feature. So whenever these terms
Okay.
will come, variable, independent term, features, these will characteristics. These words make same thing basically. That is basically number
Hmm.
of features. These all these words, variable, number of features, independent term, these independent variables or variable, simply variable, these will mean the same. So here you have only one variable, so this coefficient will only give one value. Okay. In the case of linear regression with multiple variable where you can have say three variable or four variable, in those cases basically you will have lots of coefficients, like it will not only theta naught and theta 1, but it will be theta naught plus theta 1 plus theta 2 theta 3. There will be lots of parameter. I will come to that part when we will be seeing the polynomial regression, or maybe I will come to the part when we will be seeing the linear regression with multiple variable part. Right now we are only focusing on linear regression with single variable. Okay. If you are able to
Okay.
understand
Okay.
linear regression with single variable, just theta naught plus theta 1 x, if you are able to understand this, you can easily scale that linear regression model to either linear regression with multiple variable or linear regression, or polynomial regression. Okay. So anyway,
Okay. Okay.
coming back to the code, this is how you can write the equation. Now, now suppose you like we saw in the previous slide, uh, previous session, that you have matplotlib, right?
Hmm.
For plotting the function, right, for plotting any data or whatever. So this matplotlib we can use to plot our data, isn't it? So
Yes.
I would like to see how this 96 variable looks like. Sorry, I wrongly quoted variable, basically data points. So I like to see how these 96 data points look like. So what I will do, I have imported this matplotlib.pyplot as PLT. So from this PLT, I will do nothing but I will scatter the data. And what is my data? My
Okay.
data is X and Y. So basically, it will make a graph with on the
Yes.
y-axis. See this type of graph. Yesterday, I have made a lot number of time I made this graph. If you remember,
Yes. Yes. Yes.
here cost, here what it was,
Area
size of
size.
flat. So the example was basically different. Here in this example, there is population, and here it is profit.
Mm.
But this
Profit.
kind of data, I mean, we have seen a lot, right, in the last class.
Yes.
So same thing
Yes.
I just wanted to show you here, that how can you scatter your, you can see the visualization part basically. So when you do this function,
Mm.
plt.show, the moment you write this
Okay.
statement, it will pop up a window in which the visualization will be done. Right. So you can see your X and Y data like this. See, this is your data.
Mm. Mm.
Good enough. So these are the 96
Yes.
data point, and if you see, there is a linear dependence between this, isn't it? The trend,
Mm.
you can easily fit a line like this here, right?
Yes. Yes.
Isn't it? Because you see, as the
Yes.
population is growing, the profit is also increasing.
Profit is
Yeah.
increasing.
So this is one of the way you can just simply visualize your 2D data. So 2D data, it is very easy to initialize. Uh, I mean, if your data set is 4D or 5D or 6D, you cannot visualize it. 2D, it is very easy to
Oh.
visualize. More than 3D, you cannot visualize. 3D, you can still visualize. Like
Mm.
if you remember, sometime we have to make 3D, so we will do something like this.
Yes. Yes.
Yeah. So
Yes.
this way you can at least visualize 3D, but still it is
Mm.
not the perfect 3D. But yeah, if you can rotate this box, you can easily visualize 3D, right? But again,
Yes.
3D visualization is also little tough, little tricky. You have to understand the matplotlib clearly. Uh, yeah.
Mm.
So so as of now, you understood, right? PLT.scatter, this thing is there, right? Now I want
Yes.
to,
Yes.
I want to see how the line is fitting, because right now what I can see is the scatter data point, isn't it? So I
Pattern.
want that I
Yes.
should see the fitted line. So line fitting means what? I yesterday we saw that once you got the theta naught and theta one, you got this theta naught and you got this theta one.
Mm.
So
Yes.
then you can predict your data, isn't it? Once you got
Yes.
the best theta naught and theta 1 for all the 96 values of x, you can at least
Mm.
approximate the y, isn't it?
Yes.
Y predict,
Predict.
isn't it? So
Yes. Yes.
what I am going to do is, through this model, through the same, this was the linear regression model, right? If you see the methods,
Mm.
what are the functions it's supporting,
Mm.
the same example like oops I have given, the object oriented programming I showed you, where you have a student class
Yeah.
and you have the attribute id and name, and you have some
Mm.
functions like get roll number, set roll number, get marks, something like this. Similarly, it has the method fit, which we have used here
Yes.
for training. Now again, similarly, it
Yes.
has a function called predict, isn't it? So
Predict.
it will predict the
Yes.
linear model. So now we will be using this particular function for predicting our data points. So just for
Okay.
approximating this y hat, how? I am calculating this. See, model dot predict.
Predict.
Now this model, in their attribute, it knows the theta naught and theta 1. So what I need to supply x. I just need
X.
to supply x and I will call it as a y predict. Good enough? This will be
Okay.
the predicted value. Okay. Now once I have this predicted value, so two things I have shown you in the initial session. One is plt.scatter and one was plt.plot, isn't it? If you remember, I have
Okay.
shown you two things. One was scatter, which will just scatter the data point. One was plot. That function will basically join the dots and form line, right? Whatever
Hmm. Okay.
dots will be there, it will uh, find the line. So what I am going to do, I am going to plot this x, but instead of y, I am going to plot the y predict, right?
Predict.
So if you see here, basically what I am going to do, I am taking this x, but in here I am taking y hat. So when I was taking y, my data points were like this, right? When I was taking y. But now I am not taking y, I am taking basically
Okay.
y hat, which will
Hmm.
make this data point in a single line. The approximation
Okay.
of these points will be something like this, isn't it? So I will show you.
Yeah.
Yeah. So can you see the line
Hmm.
which has been fitted? This line has been fitted through the predicted values of these points only. What I have done, I
Hmm.
have predicted on the x-axis whatever the x was there. I have predicted the y,
Hmm.
the predicted y by putting the x into this equation. So and then I joined it. What I will do, I will scatter this also. Then I think you will have a good visualization. I mean, you will come to know that how what it is actually doing. See, can you see this line?
Yes. Yes. Yes.
Basically, all these points has been projected to this line. All this point has been basically approximated by this equation of line. By this equation of line, you are approximating all these 96 points, and thus it is forming this line. So when I will instead of a scatter, if I do plot function does what? It will join these lines, the predicted 96 line, and that's why when you plot this, basically you will get a line joining all of them.
Okay.
Okay. So,
Okay.
so this is how you can visualize that, and see any case. I mean, in even in real world, in some data, in some server kind of application, or so what are the computing resources being used? How much heat is generated? So depend. Suppose just a simple example. I am telling you, you have to predict the amount of heat generated. This is a real life example I am going to quote, but of course, I am still quoting just an example of linear regression with single variable. So
Okay.
people do this thing actually, that how much heat will be generated depending upon the workload, or how do you define workload? Depending upon the
Process.
processor usage. So
Yes.
if the processor usage will be more, the heat will be generated will be more. This is a very simple scenario, and this is definitely be the case. Will be the case when your processor usage is
Yes.
going to be high, your heat is going to be high, isn't it? Now, you see, this has a very good linear dependence. I mean, if you see the data points in a server farm, or in a big company, if you see where the servers are put,
Hmm.
once the workload increases, the heat will also
Hmm.
increase. So it carries a linear dependence. So in these type of application where there is a clear cut linear dependence of independent term on the dependent term, in these type of application, linear regression is very successfully used. Still, again, I am
Hmm.
reiterating my point. still I am using single variable only, case only. There can be another scenarios which can lead to the heat generation. So when you do linear regression with multiple variable, you basically uh, you basically consider two or more variables, okay, contributing to the cost or contributing to the heat generation. Okay, that we will of course see another
Mm,
example. So this way you can actually visualize also, isn't it? Now, if I now from here, if I ask you that can you calculate the cost function which is coming?
yes,
Can we
1 by
calculate the cost function?
y predicted
Uh-huh.
minus y actual square.
Yeah. So can we do this? We calculate the cost function? I mean, see,
Yes.
after the fitting, after everything was done, what
Mm,
what was the error which has come? I mean, what is the error term basically? What is the minimal cost gradient descent has achieved while fitting this data? So that you can of course calculate. See, I will try to make things. I mean, I will try to write this equation in here. So that's what I wanted to tell you. I mean, whenever these kinds of equation will come, you don't have to worry about it. That's the powerful thing about Python. You can write these
mm.
equation in a vectorized way, which you cannot do
Oh,
it
okay.
with C or C++. So so uh,
Yes.
so what I will do, see, I'm going to print the cost function, or I will say it a error term. Okay,
Okay.
and how am I going to predict this? See, I mean, how I'm going to calculate this? See, this is basically, do we
Mm.
have this y predict and y with us?
Yes, we have.
Yeah. So what I'm going to do is y pred minus y. This is our first case thing which we have
Okay.
wanted to do.
Okay.
Now we will square this term basically. So I have shown you, if you have a array, uh, like when we did last time in
Mm.
the previous session, we see that if you have array, say
Mm.
any array,
Okay.
say 2 by 2 array if you have, and if you just
Mm.
see, this is the array, right? Okay, I will take it into maybe z. This is
Mm.
array, right? If you do this, it
Mm.
will square everything. See,
Let's square everything.
980, right? So this will
Mm.
square, the things, isn't it? This
Yes.
thing will square that. Now, now you have to do basically sum. You have to sum over all the data points, isn't it? See, you have to sum over.
Okay.
So I am using
Some. Yes.
lp.sum. Now finally, I have to divide it with 96 points
Mm.
because this 1 upon n, right? So I have to divide it with this. So if I run this program, hopefully I will get the error term here.
Okay.
This is my cost function. So this is the minimum value which gradient descent could achieve. And this, if this is zero, then almost all the points is exactly matching with the predicted. So it is never zero, because you cannot pass a line which passes through all the data points exactly. Okay. So
Yes. Yes.
yeah. Now, now this equation seems so simple, right, to write, but actually, if you go through any other programming language, not R or not MATLAB, but if you will go with some other programming language, this is actually difficult to implement. Why I am saying difficult to implement? you will have to write a for loop for this, because this y predict is basically an array. It's an array of 96 values. This y is also the second column of the text file, basically the actual y, the actual profit. So this is again an array. So this array minus array, the whole thing is just being done by this code. And then the exponent also, the squaring thing also you can do. So in just one line you can do a lot of things like this. But this thing, was not possible. uh, this thing was not possible, initially. So if you see here, this y is an array, and y is also an array of 96 values, right? So, but
Yes.
still we are able to do this array operations, uh, directly in by this particular code, and then also we are able to accommodate these scalar values. So that is why, Python is called very flexible, or say loosely coupled language, because
Mhm.
you do not need to define anywhere int or float or anything. The interpreter will take care of it. So I mean, the scientific community, those who have background of physics or chemistry or something like that, they find they had, easily accepted this language. Uh, because this seems very easy to, whatever you are writing in mathematics or something like that, you can just code it. So this is a cost function. Now if you see, in sklearn also we have the similar kind of function. Okay, that is basically import sklearn dot metrics. So what I will do,
Okay.
yeah, from sklearn dot metrics import, there is something called as mean square error. What it's called? Mean square error. This one.
Okay.
So if you remember yesterday, I told you that this particular error cost function is also called as mean square error, isn't it?
Yes.
Why? Because this is an error between actual minus predicted, and then this is a square, and this is, you are taking the mean, isn't it? So this is basically a mean
Yes.
square error. So in sklearn, they have already implemented this mean square error cost function. Okay.
Mhm.
So if I
Okay.
print here directly, print mean square error is equal to, now what I will just call that function mean square error. You have to give the y true and y predict. Okay, so y and y
Okay.
predict. This you have given, and you just print it. See this mean square error have come.
Mhm.
This is exactly similar to what we have implemented,
Okay.
isn't it? So this I just showed you so that, to verify that even our implementation is correct. Okay.
Yes. Yes. Yes.
So our implementation is also matching with the scale and metric. If you will see this particular function, the same implementation, whatever we have done here, same thing will be there also. Okay. So
For this implementation, we need to do fit X and Y also. We need to go this step by step. Like first we need to do fit,
to to,
then we
to,
need to go for model.
to calculate this mean squared error,
Yes.
see, how will you come to know about y predict? What is y predict? So y
Yeah.
prediction I am getting
I
from
should.
here after predicting through model. Now, once our model is
Yes.
trained, then only we are going to get this y predict, isn't it? So,
Okay.
yeah. So in that case, this linear regression and fitting, everything you have to do. Then only you will
Okay.
get y
Okay.
predict, and then only you will get this mean squared predict, mean squared error. Okay.
Okay. Okay.
So this is a particular, a typical Python example for linear regression. What else I will
Can I
show
see the
you? Yeah. Yeah.
Sorry, can I see the body of that function, mean square error function,
Yeah, sure.
in
Yeah, sure,
okay,
sure. So what you have to do, any function you want to see, just click on that function,
mm,
right click it,
okay,
go to definition.
okay,
So this is the see. Can you see the path here?
yes,
This path is where I have installed my Anaconda 2, C user Abhijit Anaconda 2 live site
mm,
packages sklearn matrix regression. So when you do here,
mm,
see, when you do here sklearn.matrix, it means
mm,
there is a package called as sklearn. In
okay,
that there is a folder called as metric, again a sub package, and in that you have a
okay,
class regression.py. Okay. So
okay. This again Python code, Python file,
yes, yes, yes. It's completely a Python
regression of
file.
pi.
Yeah, yeah. It's completely a Python file
Okay,
where in this metric,
okay.
in metric relation.py, you have this particular function. So what I will do, I will again go to definition. Oh shit, what happens? So anyway, so yeah, so this mean square error, can you see here?
Yes, yes,
So if you see this, these are just the comments. I mean, you can just read. This is the same thing which is written, which will be written in the Scalar on website. Okay, so the same thing they will put here as a comment. You see, can you see this particular function? This line number 238.
yes.
So y true minus y predict square they will do, and then they will take average. So they have directly taken
Mm,
average, and in
mm,
here what we have done, we have taken the sum and then we have divided it by 96 in order to get the average.
yes,
So that's the little difference, but mainly the output error they give it like this. Okay,
yes.
they will calculate it like this. So you can see that. Okay, my Python exe stopped working because I have accessed some. When sometimes it happens, I don't know why, but I
Mm,
mean, sometimes it's the permission issues are there because you have installed something over there with administrative control, so it won't let you, read the libraries like that because you can
okay,
directly,
okay.
yeah, because otherwise what you can, I mean, you can easily change the codes also,
Mm,
right, of the libraries. If you see,
yes, yes, yes.
you can change the
Mm,
library codes also. So that's why they will,
mm,
in order to prevent that, they will not allow you to directly read from there. So many a
okay, okay.
times this problem occurs. It is in fact better to go there and you can see just in a notepad. Okay.
Okay.
So as of now I am showing you the test. Also, I just wanted to show you something. So this is a typical example of how you apply regression, right? Now, suppose some new data came. So what I will do, I will take some help from here, this website. I mean, sorry, this code which I have developed. I hope this thing will quickly make sense to you because this is just a, yeah. So testing the linear regression model on new unseen data. Okay. I have done nothing. I have just created a test set of three values. These are the three values I have kept. These three values are nothing but the population of the city. Population? Yeah, population of the city in thousands. Okay.
Population. Yes.
And through this
Okay.
X test, I am predicting the same thing which I was doing on the training data 96 value. Same thing I am doing on the new data, test data. Okay.
Okay.
And then this is the predicted values for this. So if this is the population, what is my going to be my cost? If this is the population, what is going to be my profit? I mean, here we are basically estimating the profit. If this is the population, what is going to be the profit? These basically this is in thousands maybe or lakhs maybe in population. Okay.
Mm-hmm.
So if I run this, you will get to see this. See population, this predicted
Correct.
profit, this. From where these values are coming? This value is basically coming from this. You have predicted these three values. So what will be? So what it does? It does nothing. It will just put this 6.7 in place of x. Okay.
Mhm.
It will put this
Yes.
6.7 in place of x, and it will calculate the value. The value will come like this, 3.9. You can in fact quickly put this value and check. See, 6.75 if you will put here, multiplied by 1.2, it will come out something like 8. 8 or 7, right? 8's 8. Huh? I mean
Okay.
6.75
Okay.
into 1.2, it will come 8, and then minus 4, so it will come 4. Isn't it?
So, so this is Y predict.
Yeah, this is
3.97 is the Y predict.
yeah, this is
Y predict.
yeah, this is basically your predicted profit. Okay?
Mm. Yes.
So
And mean square error is 6.91.
mean square error is there 6.91.
So
That
in
has come from
9.
yeah, that has come after training. We have seen that what is my
Mm.
error term in the training data, 96 data points.
So there is a relation between predicted profit and mean square error. Like we have to neglect mean square error from predicted profit
Yes,
to
yes,
get more accurate value.
yes. See, this is just the thing. I mean, here we have nothing to do with this. This is a training funda.
Yes.
So when we saw the gradient descent, what we saw that
Mhm.
initially you take random theta naught and theta 1, right?
Yes.
And then in while loop, basically you have to iterate through the j previous and
Right.
minus j current. If it is greater
Right.
than some epsilon, you will be go on updating. So here we saw we will calculate this predicted. I mean, whatever cost function we will be there, we will calculate this. How? With y predict minus actual y
Why?
squared over and mean
Square
over,
root.
right? Just an
Mhm.
example I'm saying. So that this thing, this cost function or the error term, basically this mean square error, which I am basically printing here, this has
Mhm.
this is the minimum error which GD, gradient descent, achieved while training.
Okay.
It has nothing to do. This is
Okay.
just to show you. Okay.
Okay.
Right
Okay.
now it has
Okay.
nothing to do with that. This is the population which right now I am predicting. Okay.
Okay.
I mean, with this population, you will predict this. So similarly, you can have something like if this is the processor usage, you can the heat generated will be this. So you can predict on new data. See, whatever it has predicted, I am just taking a for loop. Okay, I
Okay.
am just taking the for loop. In fact, I will write this code again in order. This you understood, right? This is just the table. I mean, this is just this thing which is getting printed, right, with a tab.
Okay. Okay. Okay.
Now here I am just taking a for I in range. Range will give you what? See, if I do range 5, it will give me 0, 1, 2, 3, 4, right? So in
Right.
range, say what is my
X.
x test? X test
X of test.
dot shape 0. Shape 0, I have told you yesterday what is shape 0. If I take a numpy random dot rand, say 5 comma 2 or say 5 comma 5, right? So if I take this particular
Mhm.
value
Mhm.
and I do z dot shape, the shape 0 will be 5 and shape 1 will be 5, right? So similarly the shape 0
Yes.
will be 3, this one, and shape 1 will
3.
be 1. Okay,
Yeah.
so as I have three values, this was the case. Now I am just printing the first the x test. What was my population? So I comma 0. See, I is
Mhm.
basically what? 0, then 1, then 2, then 3, then 4. So it will be like 0, 1, 2. Three values are there, na?
Mhm.
So it will iterate three times.
Yes.
So this is my basically
Yes.
my population. Now I will put tabs, two tab I will put, and then I will print my predicted values. So what is the predicted values?
predicted
Again, the ith iteration and the
model.
first column. Good enough? So you can place these
Okay,
values
yes.
over here, and you will sorry, if you will place this 4.5 here, you will get this
Mm.
1.24 actually. Okay. So,
Yes.
so that's how it goes. So right now, till now, what I have shown you, I have shown you how to read the file, how to read your data set. I show you how to make the independent variable and dependent variable arrays, and finally reading it through
Okay.
the file. Then I showed you how to train the model, linear regression model, how to print the equation of line. Then I told you how can you predict on the data. I mean, how can you predict on some new data, or the same data? How can you plot or visualize your linear regression? And then of course
Mm.
I showed you this, how to predict on some new data.
Okay.
So at least this much thing you should be able to do whenever you are dealing with linear regression model anywhere.
Mm.
Okay.
Mm.
I mean, see,
Okay.
I am trying to show you all the aspects of linear regression which we have studied, how you can show
Mm.
them through the Python code. Okay. Now,
Okay.
now just in the same example, if somebody asks you that this was the 96 data point, your linear regression worked fine, okay, like it predicted and okay, we visualized it, those things are fine. But can you tell me how many points it predicted correctly?
Okay.
How many points out of 96 it actually predicted correctly? But the problem with linear regression is it won't predict anything correctly. There will be some little error. You see, this line is not predicting even a single point exactly. See, you will,
Mm.
whenever you are doing regression, whenever you are doing fitting, you cannot fit
Mm.
all the data points with a single line. Okay,
Mm.
that's the problem. Your error, somewhat error you will get always. So how do you define
Or
your, yeah,
yeah, or it might be there is one correct point. It might be there which is nearby
yeah. Of
the
course,
correct
you
point.
can, yeah, by seeing these points, you can say that some points are lying. But the point which I
Yeah.
am trying to make here is something different, little different. In
Okay.
linear regression, you never, make this statement that how many predictions you were able to make correctly, because there is nothing like
Mm.
correctness in linear regression.
Okay.
What statement you
Okay.
can make instead? Instead, you can make this statement that given that my tolerance limit is 2 lakhs
Mm.
plus minus 2 lakhs, then tell me how much prediction you did correctly. You have to define plus minus tolerance. Suppose you are
Okay.
building, suppose you are building an application for a client where the client says that you have to tell me, you have to predict the amount of heat generated in my server, on in my server room,
Mm.
okay, or I mean with my servers, how much amount of heat is generated. So, and he gives you lots of
Okay.
historical data of the workload and the amount of heat generated. Now you did linear regression very fine, and yeah, so then the client asked you that how many data points you were able to predict correctly from the historical data which I gave you. So you will
Mm.
ask him that tell me your tolerance limit. I mean, if I say that for this particular workload, this much is going to be the heat. Suppose H is going to be the heat. If the heat is say maybe 5 watt plus or 5 watt, I mean, this is the unit of heat which I am saying watts, right?
Mm.
You have kilowatt or watt, whatever it is. So if I say that
Okay.
if your heat is going to be plus 5, will it be tolerable to you? or if the heat predicted will be plus or minus 5. So in this range, if I can predict, so is it feasible to you? Will it be tolerable to you? So client will say, yeah, plus minus 5, what I do not care. I mean, it's okay. Nothing blunder will happen even if you are predicting plus minus 5 heat. Okay. We will put some
Okay.
threshold for the alarms, but you can keep this tolerance limit. So that's what I'm trying to say. It will never be the exact prediction in linear regression. You always have to tell the tolerance limit. And then you can tell what is the accuracy of your system. Okay?
Okay.
So what
Okay.
I will do, I will show you again some equation, and I will show you what actually I'm doing here. I will try to uh, calculate the accuracy. Okay? I will show you how
Okay.
you can calculate the accuracy also. Okay. Yeah. So the accuracy you can calculate like this. See, your predicted value minus your actual value. The actual value is the historical data what your client gave you. And this is the data which you have predicted through your model. Okay.
Hmm.
You
Okay.
subtract this. I am not doing the squaring and all. Just think this is absolute subtraction, absolute error. This is norm 1 error. Okay, this is a standard error basically you can say. So I am going to just take the difference, that how much, see, suppose you are predicting 5 kilowatts and your system is predicting 5.1 kilowatts. So the difference will be zero point 0.1 kilowatt. So this is the basically the absolute difference. And then you take the absolute. Absolute means even if it is negative, you will make it positive. So basically,
Hmm.
what is what is this? This is 2. What is this? 3.
Three. Yes.
This is like a mod, right? I mean, mod, or what do we say?
Modulation.
Yeah. So
Modulation. Yeah.
yeah, if it is minus 10, it will make it 10, right? So that thing basically
Yeah.
I'm going to achieve it through this function ABS. So if the
Yes.
difference, whether be the plus error or minus tolerance, I mean plus tolerance or minus tolerance, if this absolute I am getting, if this thing is less than 4, in this particular
Hmm.
application you have the problem that depending upon the population you have to predict the profit. So the
Yes.
client said that plus minus 4 lakh I do not care. If you are predicting that I will have 20 lakhs of profit, and even if I had 24 lakh profit or I just had 16 lakh profit, I am okay. So
Hmm.
what you are
Okay.
doing, if the difference between the absolute error basically between what you have predicted and what was actual is less than 4 lakh, so it's basically within the tolerance limit, then you some such data. I mean, suppose out of 96 this condition was true for say 80 points. So
Hmm.
you sum up those 80 points. So
Okay.
basically you will sum them up. So this whole thing will give you 80. And 80
Okay.
divided by 96 will give you the percentage. Okay.
Okay.
So if I calculate this, you will get the accuracy something like 88%. Okay. You will
Okay.
get accuracy how much? 88%. Good enough? See.
So 88% point are accurate by given tolerance.
Yeah, yeah.
Is that statement?
Yes. My basically on the historical data, I have proved that my linear regression is 88% accurate if your tolerance limit is of 4 lakhs. So you always, if I will put this tolerance limit to just 3 lakhs, suppose, my accuracy may go down because now I have to predict very well. So my accuracy is now 79% only.
Hmm.
If I say that no, I will not at all, maximum I will tolerate 1 lakh. So your model will be, just performing maybe 29% accurate.
Okay, okay,
So this is how it
okay.
goes. So basically, until the point which I want to make here is by showing this, that until and unless you have a linear relationship between the feature X and the Y outcome, linear
Hmm.
regression is not going to work. You should have the linear relationship, then only it will work well. Okay. So if you will keep your tolerance limit 5 lakhs, it may go up to maybe 92 or 93% accuracy. See?
92%.
Yeah. So this is, I mean, this is a vague way of defining the accuracy. Why I am saying vague? Because it is not foolproof formula. This factor will depend
Hmm.
upon the client, isn't it?
Hmm. Yes, yes.
So that's what we are trying to do here. Okay. Now this sums up the linear regression part. There is one more thing which you will hear more often. I am including lot of terms here, but yeah, this will help you when you will be actually seeing these terms, maybe with some software, or maybe if you will work on linear regression in some project, you will be listening this R square a lot. If you
Okay,
discuss this linear regression with any guy who knows ML, or who is a statistician, or who is doing linear regression and all, he will talk about
hmm,
this term. I mean, mostly they will talk about these two terms, because these
okay,
two terms actually tells you about the quality of fitting, the quality of your model.
okay,
So this mean squared error is basically the cost function, which tells you that how close it is, how close it has fitted to your actual data points. If the
okay.
mean square error is zero, it means what? If the mean square error is zero, it means it has exactly perfectly fitted the data points. That
So
will
all
never
point
go
is
wrong.
matched
Yeah, all point is
in
matching.
this.
Yeah.
Okay.
Suppose your data itself is like this. Suppose your data is like this.
Hmm.
Then when you will perform the linear regression, it will completely fit it 100%. Then
Hmm.
your J
Yes,
will become 0.
yes.
So this tells you about the quality of fit you have done, mean squared error.
Hmm.
And what is R2 score? This also we will see. This is the R2 score, right? I will show you what is this R2 score. This R2 score is basically, I will tell you, this R2 score is basically, uh, uh, it's a range between 0 and 1. It's a range between 0 and 1. So
Okay,
the more R2 score value is towards 1, the best is your model. And if your
okay,
R2 score is towards the 0, the lower values, it will be the worst model. Your R2 score should
okay.
be towards 1. Okay. In this case, your R2 score is 0.76, which tells that your model is good enough, fair enough, fair enough to
Hmm.
capture the linear dependency. Okay. Now you will ask, what is this actually R2? So I will tell you what is the
Hmm.
R2. R2 is basically nothing but, for all the data point I to n, uh, what you do, whatever is your predicted value
Hmm.
minus whatever is your
Actual.
actual value, divided by, again, whatever is your predicted value minus
Hmm.
whatever is your y mean. Hmm.
Actual.
Yeah. No, it's not actual. It's the mean.
Okay.
Okay. So the denominator is basically this is your actual
Okay.
and this is your actual.
Okay.
So suppose I will just take an example that your actual was say 1000, 750, 800,
Mm,
and you predicted it
mm,
as say 990,
mm,
760, and say
mm.
900. So
Okay.
predicted minus actual you have to do,
Mm,
and then you have to do actual minus
and
mean of
mean
actual. So what will be the mean of this? It will be somewhere around um,
800,
800, right?
850.
Yeah, so you
Mm,
subtract 800 from this, 800 from this, and 800 from this. And then this thing you sum it up. So whatever this
mm,
thing will come, you just sum it up, this value. And this is basically your error, predicted minus actual. The one which we usually see. So this when you
okay.
divide, it will always come between 0 and 1. See, this y actual minus y mean is the worst thing which can
Mm,
happen to you. Is the worst error basically which can happen. Why I am saying
mm,
this like this? Suppose you have a linear dependence like this. Ah,
okay.
what will be the average of all these data points? Somewhere here. You don't you agree? I mean, you agree or not?
Average of on y-axis.
Yeah, I am saying if
Uh,
this is the data point with me,
yes,
if I
yes.
take the
Mean you mean to
average,
say mean?
yeah, yeah.
Mm,
If I take the average y, this is
mm,
y only, right?
mm,
This is basically the
mm,
predicted outcome. Okay.
mm,
So if I take the average, it will come something like this constant line, right?
okay.
So the most deviation, the worst deviation you can have is this one, which this line is having actually.
Mm,
Why I am making this line as a mean? I mean, you might be confused, but yeah, I will maybe tell you again. This is x, this is y, isn't it?
mm,
So
yes.
I am calculating basically this particular point is my y mean. All these data points,
Okay.
whatever be the y for these data points,
Okay.
if you will calculate the mean, it will come as this line.
Mm,
Okay. So and this line will pass through the middle, and the linear dependence will be something like this. So this is the most wide spread. I mean, most spread you can get. So this is the worst thing, right? This value will be very high. This
okay.
denominator value will be very high.
Mm,
Okay, now come to numerator. Now numerator is basically when you predict this line, I mean it when you fit this line with linear regression, it will come something like this, right?
mm,
So if you fit some
yeah.
this the line will come like this, right? Now this
Mm,
actual minus predicted will be very small when the line which you are fitting is good enough to pass through the values, right? Isn't it? So
okay.
this
Okay.
numerator is going to be very small. This numerator is going to be very small.
Small.
Yeah, because it is fitting it very clearly. So the error term basically it is
Mm,
basically very
it's
small
small. Mm,
in comparison to this line where your error is very huge, right? So this is
okay.
very small. Maybe I will take a new thing. So the numerator will be a
Mm,
small value, and denominator can is the worst largest value basically.
mm,
I'm just trying to give you the intuition. Okay. So if this is a large number and this is a small number, this is going to be 0. Okay,
mm, mm.
and 0. So basically the formula of r square is y minus, say y predict minus
Why
y actual,
predict? Okay.
uh, y minus, this is y actual minus y mean,
Mean.
and then 1 minus, this is also there, I forgot
Okay.
to tell that time, but this is the formula. So when this,
Okay.
when your y predict minus y actual, basically this part, if it is fitting it very well, if it is
Mm,
fitting it very well, then this value will be very small. And
mm.
this value is the worst value, I mean, is the largest error you can have when you are subtracting it with the mean. Basically, this
Okay.
is a kind of standard deviation kind of thing. No? This is the deviation basically. So it is going to be the maximum.
Mm.
So this is the large value. So this small value upon large value will be 0. See, small value
Zero.
means
Yes.
0.1, large value means say 5. What it is going to be? It is going to
Mm.
be even like this.
0.052.
So it is going to be towards 0, right? And
Yes.
anything, say 1 minus anything like 0, it will give you 1, right?
Yes. Yes.
So basically when R2 value, when R square value is 1, it
Mm.
means that this is the best fit. I mean, this is a good fit. Because this numerator will
Okay.
be very small. This numerator will be very small. This numerator will be very small. See, just like you see,
Okay.
just forget everything. Just see this formula. If this numerator is going to be small, this whole value is
Mm.
going to be very small. And then 1
Yes. Yes.
minus a small value will be a large value.
Large
Right?
value. Point.
If the line is a very bad fit in the linear regression,
Mm.
suppose where should I make the, yeah, this is the graph, suppose, or say this is the graph,
Mm. Mm.
and if your data points are
Mm.
totally separated like this,
Mm. Mm.
and if you are trying to fit a line like this, now this error
Mm.
is high, huh?
Mm. Yes.
And this error is high that in fact the mean of this data point will come like this, and even your line
Okay.
fit is also very high.
Mm.
So at that particular time, this value will become very high, and even
Mm.
your mean will become good enough. I mean, say small value. Say this mean will shoot
Low.
to say
Low.
1, and this will become say something like this.
5.
Uh, I mean, mean will of course be the worst thing, but yeah, let's say it will be 5 only. It will, this y
Mm.
predict minus y actual will be so high, it's a so bad fit
Mm.
that it will almost be equal to this value. So then this will come,
Mm.
so it will almost be near to 1. So 1 minus 1 will be 0. So that is a very
0. 0.
wrong fit. This whole thing I just wanted to give you the intuition about R square. You don't need to, I mean, of course, you need to understand the logic, but even if you remember this
Yes.
funda that R square
Mm.
ranges from 0 to 1, where the best score
Mm.
is 1 towards 1 and the worst score is towards 0.
Mhm. 0.
So this completes our linear regression with one variable. I mean, from my side is completed. You can ask me any questions or anything which you would like to ask. What I will do, I will send this particular file, whatever I have made.
Okay.
See, R
Okay.
square I have tried to put it in the comments here.
Okay. Okay.
Okay, you can read it from there. This file I will maybe, I mean, uh, share with you. Yeah. So
Okay.
if you have any doubt about any code or anything, you can ask.
So in linear regression,
Yeah,
we cannot means we can predict one value based on the given parameters.
yeah.
Okay. So if I want to predict a value, I have to pass the parameters. So it will give me predicted value
Yeah.
on which is nearby my mean line. It
Uh,
is take that point or it is create another point or another value.
uh, okay. So
You
what
got
you
my
mean to
question?
say? No, no, I didn't get actually. What you mean to say that
Okay,
you
okay.
have this one parameter. Parameter. See, I call parameter as theta naught and theta one. You are calling this
Mm,
size of flag
this
or
parameter,
something.
yeah, yeah.
Okay. So you can call
Yes,
it
yes.
feature. Okay. So
Feature.
what you
Okay,
are
sorry.
saying, yeah. So what you are saying that we here
So
in linear regression we are predicting our
my
cost. Yeah.
my line is generated.
Okay.
It will match the line.
Yeah.
So whatever I'm going to predict basis on the size.
Yeah. Here, suppose this is the value which you are going to predict. For this value, I want to predict
Mhm.
the cost or
Cost.
surprise.
Okay.
So basically, this value I will pass it to this line
Mhm.
wherever it is matching, and this will be the cost.
Okay.
Okay. And now, when I am saying I am graphically pointing it towards here, it what it means? When I am basically projecting it on this line, it means that I have the theta naught and I have the theta one and I have this x. So if you
Uh-huh.
want to predict
Okay.
on this value, just put this value here.
Okay.
And then this value
Okay.
which
Okay.
you get is basically nothing but this value.
Okay.
Yeah.
Okay. Got it. So I can get coordinate for this line, like which point it's intercept or which point is matches.
Yeah, so for this line, what you get is that, say, how do you define a line? You define a line by theta naught and theta 1. So you will get the
Mm-hmm.
coefficients and you will get the
Mm-hmm.
intercept term from the model. These are basically the attributes. These are
Mm-hmm.
basically the attributes of this. Okay.
Yes.
I
Yes.
mean, if you want to know which point it exactly matches, that you have to check with the
Uh,
predicted and this thing. If you go here and in the accuracy, where was the accuracy? Um, I somewhere I have printed the accuracy.
six. No, this is
Another
a
file.
different file. Like.
Yeah, actually, yeah. So I will show you. See, here you this accuracy
Mm-hmm.
you make it 0, or you say it equal to 0. Uh,
Mm-hmm.
so if such is the case, this will tell you that whether it has actually the accuracy is 0. I mean, it is not passing through any of the point. See, let's say make it so point 0.5.
Mm-hmm.
14%. So 14% of this data, 96. What will be 96? So
Mm-hmm.
basically maybe 12 point it is passing very nearby.
Okay. Okay. Okay.
Okay. So see, in
Okay.
linear
Okay.
regression, that's what I told you. Na? In linear regression, you never bother about how much data point it is exactly passing. Because the regression problem
Okay.
naturally comes with some tolerance limit. Okay. Some plus minus limit. So
Okay. Okay.
you always go like that. You will if you are thinking that it will exactly match your point,
Mm-hmm.
that will not be the case. See, linear regression is only used for prediction, is only used for estimating some value. So that is why when I talk about linear regression is always, it is also called as real valued prediction.
Mm-hmm. Okay.
Linear
Okay.
regression will never do classification things like categorizing a cat or a dog in an image. It will never do things like that. It will always estimate something, like it will estimate the sales, it will estimate your profit, it will estimate the price of house, it will estimate the amount of heat generated, it will estimate some value, it will always estimate some value. Okay.
Okay. So there is some other features which will impact this
Yeah, the
calculated
cost
prediction
or the price. Yeah, yeah.
price. Yeah.
There can be other features
So
too, right?
yeah. So how we consider other
Yeah.
features also?
So that is what actually I was coming to now after this Python example. That will be, considered with linear regression with multiple
Hmm.
variables.
So we have to provide data points for that other
Yes,
features also,
yes,
or
yes, yes. You have to provide that. Now I will tell you a case that is basically the Python example. Also, we will be seeing on that. Or I have uploaded. If
Mhm.
you have seen, I have uploaded the text file to you. That is basically,
Mhm.
suppose you have been given the size of flat and number of bedrooms, because the number of
Mhm.
bedroom is again a contributing factor to,
Mhm.
it's again a
Cost.
contributing factor to what your uh, cost is going to be.
Cost of
So yeah, so
okay.
this is, if this is the case, now this is exactly
Mhm.
the case which you are talking about, that if there can be some other feature also which is contributing to the cost, or rather than cost, not to confuse with cost function, I will use the term price. Okay. So
Okay. Okay.
So suppose these are the three values which you have been given: size, number of bedroom, and say if size is 1000 and number of bedroom is 2, your price is going to be say 20 lakhs.
Mhm.
Huh,
Okay.
20 lakhs. Now if size is
Okay.
say 2200 and your number of bedroom is 4, it is going to be 81 lakhs.
Okay.
Like this is the feature. Okay. Suppose the size is
In
50
this case,
3
so in this case, we know the bedroom number of bedroom.
yeah, yeah.
But
So if,
suppose there is feature
mhm,
which we don't know.
yeah. So in those cases you cannot include for training. For training you
Okay.
must have the historical data. For training you must have the
Okay.
historical
Okay.
data of the sales which
Okay.
has been done previously. This is my training
Okay.
data on
Okay.
which I am going to, do linear regression. Now,
Okay.
till now,
Okay.
what we were doing, we were simply, making an axis. Here is your x, here is your y, and here are the data points
Mhm.
which you are going to fit. But now, as the number
Mhm.
of variables are increasing, it will be little tough to visualize
Mhm.
this. Don't you think so?
Mhm.
Because
Mhm.
how are you going to make the axes? See, this is going to be size. Then this
Mhm.
is going to be say price. Hmm.
Mhm. Yeah.
Now you have to find some third axis also, which will be telling number of bedrooms,
Bedrooms.
right? And then in this
Mhm.
particular, basically in this particular, uh, you see, in this particular 3D space, you will be
Mhm.
visualizing your, whatever you can do. Like this, in this 3D space, you can visualize your. So if suppose number of bedroom, suppose number of size is this, number of bedroom is this.
Mhm. Okay.
So at this with this value, what is going to be the, price? So that you have to look it
Yes.
in maybe some 3D. I mean, this point will also be becoming 3D, and then you have to maybe look it in 3D. And such data points in 3D, you have to fit a plane. So if you have lots of 2D points, so now in this 3D space, you will have some data points, and that data points you may have to see. If I show you in a little clearer way, see, this is basically a 3D space where you will have to, where your data points will be like this, lying in
Mm.
this whole volume.
Mm.
And then
Yes.
maybe you have to find the plane, a kind of plane which will be dividing your data. I mean,
Mm.
sorry, not dividing, basically which will be fitting your data points
Fitting.
in the linear way, in the that linear relationship basically. Okay, so I will try to maybe visualize you a little bit, but yeah, that's the case. So how I can mathematically formulate this thing? Yeah, so how I can formulate the mathematical part of this? If you see, if you now your hypothesis will be defined as theta naught plus theta 1, huh, and x1. This x1 is what? Size,
Mm.
plus theta 2 x2. This x2 is number of bedroom. Did you get my
Okay.
point? So this will become the equation of line now. And even if you have 10 such features, this thing will go on increasing like this.
Okay. X4.
Okay. This particular equation where this is defined by an intercept term plus coefficient theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 4 x4. This particular equation is called as linear regression with multiple variable,
Okay.
where you have multiple variables: size of flat, number of bedroom, say location, say type of furnishing, lot of things you can have. Okay,
Okay.
so we will be seeing a practice example on another data set, which is ex data 2. Can you see this data set? Here I have a historical data, or you can say the training data, the previously known data. 47 such sales observations, sales data I have, where I have the size of flat, I have the number of bedroom, and then I have the cost of flat, on the price of flat on which it was sold. Again, size, number of bedroom, cost. Size, number of bedroom, cost. Size, number of, like that I have 47 data points again. Okay.
Mm.
So on this data again you can do the linear regression with multiple variable in the similar manner as you have done linear regression with single variable. Okay. So now the hypothesis has changed. I mean, I have basically extended the hypothesis, nothing else. Nothing will change. Your gradient descent, your everything will remain same. So now what is your cost function when you have j theta naught to j theta 4, or say 10, or say 20? Then this will be same thing. This is basically your y predict, basically this thing,
Okay.
minus the actual y, basically this thing, sorry, this thing, actual y,
Mm.
then I equal to 1 till 247, 47 data points I had, 1 upon 47, basically n. squared over. This the cost function is same. The cost function is not different. Okay. But only thing is now y predict. Initially it was calculated simply by theta naught plus theta 1 x. Now it is calculated by this whole thing. Okay.
Yeah.
Enough? So
Yeah. Yeah.
so this is how the linear regression with multiple variable will be done. So the formulas will remain same. If you see the gradient descent update parameter, it was earlier something like this: theta naught minus alpha, and here you had theta naught plus theta 1 x 1 plus theta 2 x2 minus actual y. This was predicted, this was actual, isn't it?
Mm.
Into 1. Theta 1 will be updated as theta previous theta minus alpha into theta naught plus theta 1 x1 plus theta 2 x2 minus y into x1. Theta 2 will be predicted as theta 2. Same things. That's what I am always telling, that it is just the extension, nothing has changed literally. This x1 and x2 is coming because of the partial differentiation of these terms.
Okay.
This one is coming because of partial differentiation of this term. This is coming because of partial differentiation of this term with respect to theta 1. This x2 is coming out because of partial differentiation of this because with respect to theta 2.
Mm.
So the same thing happens with gradient descent, in the gradient descent with linear regression with multiple variable also. Only thing is uh, your thetas will be extended. Okay. Now let me show you the example of multivariable, linear regression with multiple variable. Okay. Right now I am just showing you this. Okay. We will discuss it again once you try this out with on your own maybe. See, similarly I have read this path ex1 data2.txt. I have opened it. I have made two arrays. Now initially with linear regression with one variable I was making it 96, 1 because I had only one variable, one feature. Now I have two feature. One is basically the number of bedroom and another is size. So I have taken 47, 2 and this is the prices. Basically this one, the price of the house. Okay.
Okay.
And then same line by line I am reading. But here now when you split it through comma, you will get three values, isn't it? You will get
Mm.
one value
Yeah.
this, one this, and another third one this. So like that, basically I am now pushing the first two values into x, and in the prices, basically which were my y, I am pushing the third value. Okay. And same linear
Okay.
regression I am calling, and model.fit I am calling, and I am predicting, isn't it?
Okay.
Now similarly I have written the equation of line, but now the equation of line is intercept plus coefficient 0 0 x1 plus coefficient 0 1 x2. Basically it is theta 1 x1 plus theta 2 x2. Good enough?
Yeah.
And now the plotting, actually I have tried it to show you, visualize you through 3D. So I have used some toolkit which have 3D accesses, and I have tried to, so you don't worry about this code. This code is just like that I have created for you to, in order to visualize you in the 3D. See, this is 3D. You have two features, so still I am able to visualize it through 3D. If it is there are 3 features or 4 features, I would not be able to visualize it. Because max I can visualize it through some coding is three dimensions. Okay.
Mhm.
And same accuracy, error term, mean square and R square I am calculating. So this program will seem similar to what 1D single variable was there, but only thing, so I will just run it maybe. Okay. So new dedicated, it is always good to run. See the equation of fitted line. See, can you see this? Theta naught, theta 1 x1, theta 2
Mhm.
x2. Is it fine? The equation of line, isn't it?
Yes.
Yeah, hello?
Yeah, yeah,
Yeah. Now you see the image. Can you see this image?
yeah.
Can you make out something from this? See, these are my data point. In the 3D I am trying to visualize. See, this is what 0, 1, 2, 3, 4, 5, 6. This
Yes.
axis. This axis is number
Yes.
of bedroom. And
Yes.
this axis is number of bedroom, and this axis is size of flat.
Size.
And this axis is the cost. So if you see my data point, I mean for particular number of bedroom, for particular size, you have some cost, some training data. And the linear dependency I am trying to find out with this predicted plane. This, if you see, this is a kind of a plane which I have predicted. This plane is trying to fit it. Okay. Actually, I have
Okay.
plotted it, so all the lines, all the dots has been, I mean, it has become weird, but yeah, like this, if you see from this angle, it is a straight line kind of thing, but it is not a line, actually, it is a plane. Seems fine?
Yeah.
And the accuracy 91%, 91% accuracy when you have, I mean, this value is in lakhs, right? 5,39,000, 4 lakh 91 lakh. So if I have taken the plus minus 1 lakh price, then it has shown 91 lakh accuracy. And this is the error term, which is also coming from the mean square the same similar way, right? And of course, this is the R square,
Okay.
73%. So if you see the error here, the error is huge because it's a 2D, right? See this value is 21, see such a huge values, and these values are so low values, right? I will come to this maybe tomorrow, that what does these means. I mean this axis and this, uh, so there are 2 features here. Let me make my statement more clear. You have 2 feature x1 and x2. Now values of, and this is y basically, which is the price. I am not caring about this as of now. Now values of x1 is very high. These are in terms of, in order of thousands, isn't it? And value of x2, which is number of bedroom, this is just in order of 10. So this way, I mean in linear regression, this way you cannot, process the regression model. You cannot train your regression model. You have to normalize both these features into the same order, and then you will actually perform the normal, then only you will perform the linear regression. I will come to this particular thing in detail. Even if you do not understand as of now, you do not need to, there is no hurry, no need to worry. I will discuss this thing then all. See, that's why in multiple, see, when I was doing linear regression, I passing anything into here? No.
No.
But when I am doing linear regression with multiple variable, I am passing here normalized equal to true. Okay, so you have to normalize your
Yeah.
feature. Just for information, I am telling you right now, even if you do not understand what is happening, have patience till tomorrow's lecture. I mean tomorrow's session, or maybe whenever we will be having session. So there I will definitely again start with this linear regression part, and we will finish this. I mean I will tell you in detail what is this normalization means. Okay, but yeah, but this is the way it goes in linear regression with multiple variable. You can have, I am again telling you, you can have even 10 features also, still you can do linear regression, still you can fit your, but only thing is there has to be the linear dependence. If there is no linear dependence, there is no meaning of doing linear regression. Okay,
Okay.
we
Okay.
will
Got
see a lot of such examples in the coming sessions until this regression part we are covering. So I will come up with more examples which will clear the concepts, and which will, I mean, show you more examples. I will show you more examples on the regression part. So right now we have seen linear regression with single variable and multiple variable. Still there is another kind of regression which you can say we will be seeing in next is polynomial regression. So we will be seeing that also, how polynomial regression looks like. Uh, but yeah, we will be discussing a lot about this still maybe. Uh, yeah. So that's fine. That's good enough for today.